All right, let's talk about the reactions of the alkenes. Alkenes burn dirtier, meaning they have more soot and carbon dioxide, less complete combustion due to the high ratio of carbon to hydrogen. Aromatics, those are things with a benzene ring, burn dirtier as well. Okay, so if we talk about addition reactions with the alkenes, we see that the bond enthalpy of the C single bond carbon, okay, is 348 kilojoules per mole, but the double bond is 612. So this is less than that single bond. Okay, so the double bond between two carbons makes this molecule more reactive. Okay, because that second bond is easier to break. And we'll see that some of the most important reactions of the alkenes are addition reactions, where this unsaturated bond, this double bond, becomes broken and is bonded with other elements. Okay, so then it forms a saturated compound with the stronger bonds. Okay, so for the first thing, addition reaction, we're going to use ethene as our sample. Ethene reacting with hydrogen in the presence of a nickel catalyst is going to form the alkane ethane. Similarly, if I have bromine or any halide, Cl2I2, it is going to form the dihalogennoalkane. Okay. Third reaction is the reaction with water in the presence of concentrated sulfuric acid. And let's make sure that we say concentrated sulfuric acid, and that's going to form the alcohol. And then the fourth type is with a halogen halide, which will then form a halogenoalkane with only the one halogen connected. It is important to note in what catalyst is present, if there is a catalyst, or if there is no catalyst present. The conditions of the reactions are important. This reaction with the hydrogen and an alkene is known as a hydrogenation. And then the reaction with the water molecule is known as a hydration reaction. I organized it this way, or borrowed somebody else's organization, Dr. Carrier's, because I think it makes sense and it helped me remember the catalysts. Hydrogen is the first thing I start with, and it's a nickel catalyst. And then the things top and bottom, hydrogen, smaller than water, so water goes on the bottom, making the hydration. Water has the sulfuric acid catalyst, which is larger than the nickel. Hydrogen is a smaller molecule than water, so it uses the smaller catalyst. There's no basis in chemistry for that. It's just how it was easy for me to remember, or at least easier for me to remember. Then I put the halides on either side, and neither one of these uses a catalyst. Might help you remember them, might not. All right, so what are some of these uses of addition reactions? Well, as I said earlier, hydration, hydrogenation, and then there's bromination. And I don't know if that's how you say it. All right, so pure bromine is a red liquid, but it has a yellow-orange color in solution. Since the alkene is going to react with the bromine, the test for whether an alkene is present, another way of saying that test to see if I have unsaturation in my hydrocarbon, is to put it with a solution of bromine. If there is an alkene present, it will go to a clear solution. Okay, if it is an alkane, it will not react with the bromine and stay colored. Alright, so the reactivity of the hydrogen halide increases as the bond strength decreases. If you could pause the screencast and put these in order of increasing reactivity. Okay, in order of increasing reactivity, okay, since the strength of the bond will be weakest for HI and strongest for HCl, the reactivity increases as the basically as the halogen gets larger, making a weaker bond. Okay, hydration. Ethene is an important product formed during the cracking of oil, and ethanol is easily formed with the addition of steam to ethene. Okay. Oh, and remember that concentrated sulfuric acid, or I should just say sulfuric acid, is the catalyst in this reaction. And then we have hydrogenation, which is the addition of a hydrogen molecule to unsaturated vegetable oils, and this makes margarine. Okay. And basically it just reduces the number of double bonds. Then we have addition polymerization, sorry. Okay, and under certain conditions we can undergo reactions where it is going to form a long chain with itself and many thousands of carbon atoms in this polymer. And really all that we're doing is we're breaking this bond and having an electron go to either side and being ready to bond on either side of that double bond. To make polyvinyl chloride, we take chloroethene and polymerize it with a repeating unit that looks like this structure here. And this would just have all those same units for PVC. And then Teflon, which is really just tetrafluoroethane, is the, again, breaking of that double bond and making this long chain where the repeating unit would look like this.